This is the Ditch the Glitch panel. We're going to talk to you about the ever-exciting topic of latency, which many of you will not know about, and if you do, you probably misunderstand it. So we're going to go into that. Everybody loves to talk about broadband speed, gigabit per second symmetric. That, as it turns out, isn't necessarily the most important thing. So we've got a great panel for you today, and we've got folks here. I am Jason Livingood from Comcast. I'm the Vice President of Technology Policy, Product, and Standards. And the panelists that we have today, we have Dominique Lazansky. She works on international governance and cybersecurity policy and has become an expert on things like mobile device security and standards development. And she works on a variety of projects for her company, Last Press Label, and just finished her PhD. Congratulations on that. That's never an easy thing. She's also an amateur biathlete and roller ski and Nordic coach. So as you'll find out, everybody on this panel is athletic in some way, shape, or form, including myself. Next up, we have Nick Feemster, who's the Neubauer Professor of Computer Science and the Director of Research at the Data Science Institute at the University of Chicago. And that is a long title, that's quite a mouthful. He focuses his research on many aspects of computer networking and network systems, particularly network operations, security, and censorship-resistant communication systems. He's also an avid distance runner and has completed more than 20 marathons, which is quite an achievement, so kudos. Next we have Ermin Sakic is from NVIDIA. He's a senior software engineer there. And surprising to see NVIDIA is not in the AI presentation right now, which is good. They're here. So take that for a sign of what things are meaningful, I think, in terms of networking technology. At NVIDIA, he works on QoE improvements and network routing for their growing cloud gaming service called GeForce Now, and its AR/VR streaming stack, which is going to be the next thing that really grows rapidly for them. He's also been at Siemens, where he worked on real-time or time-sensitive networks and real-time applications, and has a PhD from Technical University of Munich. And in his spare time, he runs half marathons, so he's not quite up to marathon distance yet. And reads science fiction. And lastly, we have Mike Conlow. He's the Director of Network Strategy at Cloudflare. He helps measure internet performance and build their infrastructure around the world, advocating for things to help grow the internet, which is always good. Before then, he's focused on political technology, both at the Obama campaign in 2012 and as deputy CTO. And in his spare time, he plays ice hockey and works on many hobby projects, including tending his community garden, which is great. So we've got an ice hockey player, 3 runners, and then a runner and cyclist. So lots of fun stuff there. So let's dive into the slides. I think I have the clicker here. Let's see if it, yep, that's the first one. So slide deck number 1, yep, that's it, perfect. Excellent. Thank you. So this is Ditch the Glitch. I think you recognize things like that, but you might not recognize my dog. That's my dog, Luna. Got to know her even better during the pandemic. And the first thing that you'll know, especially if you've got great internet service at home during the pandemic, you probably still had Zoom problems. You probably had little glitches. And the reason wasn't lack of bandwidth. That's a clue to our panel. So let's talk through exactly what latency is. So latency is an important thing, an important aspect of internet performance. And essentially, it is very different from what people understand it to be. And I'll explain that in another slide. But really, it says that everything we know about internet performance is mostly wrong. We used to think that more speed, more bandwidth solved all ills on the internet. And it's true, speed is very important. And it's always been a good proxy for quality of experience for users. But it is not the only key performance factor. And as we enter what I sort of call the era of bandwidth abundance or the post-gigabit era, it is no longer the primary factor in user quality. And that thing is latency. And almost every problem that people experience is latency related these days, but people don't really understand what that is. And so a lot of times when people think latency, that's sort of a nerdy kind of word, maybe better, I think, to just think delay. No one likes to wait for something. No one wants to wait for content. No one wants to wait for something to load on their screen. And if you're doing something interactive in real time, you don't want to wait for those things. And that's important. Delay is really the most important thing. Today, when policymakers in particular talk about latency, they talk about what's really idle latency. So it's when you run a round trip, like a ping packet from point A to point B, and you see how long that takes. And to use an example, fiber or DOCSIS networks might have latency on the order of 10 to 15 milliseconds. And you might think, wow, if one type of networking is 10 milliseconds of idle latency and another is 15, that's a huge difference, right? Doesn't matter, really, because working latency, which is the next one here, is on the order of hundreds of milliseconds of delay or thousands. So it could be a half a second or a second of delay. And if you think about a lot of web pages and applications doing multiple round trips, you then have all of that delay stacking up and causing real delay to the point that it's a several second delay in many cases. And that's why you notice occasional glitches in games or video conferences or what have you. So that's the key thing, is sort of reframing what we think of as latency. And so, this is hopefully about as nerdy as it's going to get. This is a distribution of delay and what the sources of the delay are. And that idle latency, that basic ping that someone runs, is really just testing the first two parts, the propagation delay. That's the speed of light on a fiber. You can't go faster unless you're maybe in outer space, which is one of those cool kind of things, but you can't go faster than that. Interface delay is that protocol like PON or DOCSIS and so on. Again, there's a certain amount of built-in delay in those protocols, but those are what they are. Really, the highest that you would see is maybe geostationary, high orbit satellite, where you might see 100 milliseconds or more. But for most technologies, you've got this negligible budget, at the left side of it. But really, the big one is the queuing delay. What happens at the internet protocol layer in a computer that's trying to connect to the internet and send packets, or in your home router or your Wi-Fi network. And that is where, from a return on investment standpoint, the network community has been focused. And that is where all of the problems from a user standpoint occur today. And so that's important. So at the IETF, which is the Internet Engineering Task Force, they've been focused on this new notion of dual queue networking. And so that's a new thing. And the first, I think, important aspect of this to understand is that on any end-to-end path, from say your house out to content at Google or Cloudflare or NVIDIA or wherever, somewhere on that path there's a bottleneck link, that link that is the most constrained. And that link is where this queue is going to build up, where the delay will become a factor. And so that is where the IETF and other networking organizations have been focused their research and development on to try to fix that. And so the great part about these standards, including active queue management, which is something that networks can deploy today, is that it can be incrementally deployed. It's not where you have to wait for everybody to support it before you can deploy, which is always good. So that is a good thing. And there's also very loose coupling. So a network that might deploy dual queue networking or AQM can do so without having to do any coordination in particular with application vendors. Very different, I think, in contrast with sort of 5G network slicing, where there's a high degree of coordination, or other things where that happens. And I think in general, the sort of way that the internet architecture succeeds is by having loose coupling. And then from a net neutrality standpoint, a lot of you are policy wonks, and for when you think about the policy aspects, you have the applications themselves that are marking their traffic, their packet headers. It's not the network doing that marking, and that's an important distinction from a net neutrality standpoint. At the same time, any app provider that can mark their traffic can do so. It's not that they have to get permission, they have to agree to some API terms of service, and so on. So that's another big aspect that is a little bit different from some existing things. And I'll mention very quickly, Comcast has a field trial of low latency networking that's out in practice right now. We've been doing it since late summer. We've seen basically a 50% reduction, in some cases more, reduction in latency, which is amazing. Really is transformative from a cloud gaming standpoint, and we think it's an important enabler for AR and VR experiences. Really any application that you can think of that involves interaction between user and a screen or a user and an AI device, something along those lines. So with that, we'll go to our second slide deck.
Question.
Yes, quick question.
Is this an open standard?
It's a totally open standard, yes. Anybody can embrace it. So, the first thing that many people have deployed over the last few years and are deploying now is active queue management. Anybody can do that. And then the IETF's new form of dual queue networking, totally open standard. The first 3 RFCs published last year. There are a few more that will publish this year. Oh, totally open. Anybody can adopt it, which is great. And starting to get built into open source. Yeah.
I noticed you don't address the asymmetric older boxes, 2 of the 3 systems where you can't have as much of an upload. And so what happens is when they reach that upload on a game, because there's multiple people gaming, then the latency dramatically increases.
That's right.
To 1,000 milliseconds if you're talking about fuse or something.
Yep.
So I think 4 is going to be asymmetrical and that's going to resolve that issue, or will they even assign it?
Even with symmetric gigabit service, you still can have high working latency because there's a bottleneck somewhere. Folks like Nick might mention this in terms of the home network being one of those places, but even the gateway outbound in a symmetric service can in many cases be the source of that latency because you've got all these different types of cross-traffic competing for network queuing. Yep. So next up, we've got Dominique, and this is the clicker.
Right. Thank you. Thank you, Jason, and thank you to all of you for coming here instead of the AI panel. And I'm going to take you on a quick tour of net neutrality regulation. Despite what Jason just said about the new IETF standard being net neutrality friendly, it's important to understand that there are very few technologists in policymaking that understand how things work and understand emerging standards. And so a lot of what we're talking about is still going to be regulated in the EU and UK in particular, and also in the US, as you're probably more familiar with, under general net neutrality rules. I'm from the UK, so I'm going to spend a little more time on Europe and the UK, but a quick. So I just wanted to point out that in the European Union, the regulation is still, the net neutrality regulation is still in force in all of the European countries, except for the UK, which had Brexit, which is why they have a different net neutrality directive or regulation and not a directive. Just wanted to remind you about this because basically this is from 2015, and this particular paragraph talks about traffic management from a technical point of view rather from preventing content or other kind of information from getting through in the service of net neutrality. It's in Article 3 if you're interested for the policy wonks. And then, of course, the European Commission last year had a consultation, and just the header of the consultations on this slide. There was a fair share campaign by various telcos in Europe to basically ask another version of sender pays, but to ask platforms to pay for build out and content, which is really interesting because I think that's a direct result, probably many of you know, from heavy-handed regulation, right? Freeing up regulation would be able to create more innovation around contracting and working with different parties, but the fact of the matter is that this is what happened last year. The European Commission had 3 takeaways, which we see also on this particular slide. We need more innovation and efficient investment, leveraging the single market, and securing our networks. So the commission, and for many of you who may not be watching this, they have one more year left of a 5-year term. There will be elections next year in Europe, European elections, and this will probably uproot and change all the work that's been done, but also change the direction, because as the world is going, it looks like most of the people that will be elected next year will come from center-right parties or right parties. So we'll have a completely different approach. So the commission's kind of slowing down their work at the moment. In the UK, this is where it gets interesting. In the UK, there was a consultation off the back of Brexit, and the results were basically, after multiple consultations, the results in October, basically turned over to industry the ability to offer premium services, specialized services, different types of uses of traffic management, both technical and for managing different, like gamers, versus other things, where they would be able to offer different rates depending on different people who want different things, and zero rating. I think the important thing here with what Ofcom, the regulator in the UK, has said is that they are not going, we also need to clarify we're unlikely to have concerns where ISPs are taking reasonable approaches. So they're going to take their hands off and look for innovation in the market. So one last slide, trying to be quick. Where does that leave us with latency? Well, I think just hearing from Jason, and we'll hear from our other more technical panelists, there's a clear misunderstanding of what latency is. Obviously, I think all of you and me just learning about it for this particular panel really doesn't understand how traffic management and how latency and the ITF standards and other standards can combine to actually even provide more efficiency. My proposal obviously would be to simplify regulation so that innovation can occur, and there can be different partnerships both with academic and other companies as well. Obviously in the US, all of you are awaiting more discussion on net neutrality coming up very soon, right? And again, in Europe, this will change significantly in the next year, but in the UK, it's going to be interesting to see what the recommendations that came out a few months ago will, play out. So that's it.
Great, thank you. Next, we have Mike all the way at the end. Do you want to pass that down for his slides?
Great. Thank you. I'm going to do a little bit of an overview, like Jason did, but I think we'll cover different ground. So back in the kind of early part of the internet, if you were accessing a website of a company, your traffic might literally go to the headquarters of the company in the basement on a server and then come back to you. And so a lot of things have changed, but at its core, a lot of what we do on the internet is a request for data. You're issuing a request from your computer. It's literally called a request for the website. That's going to go out from your router. It's going to go through a couple of routers at your ISP. And then eventually, it's going to hopefully find the content or service that you requested at the data center. And there are some places in the US, like in the Midwest and in the South primarily, where it could actually go across a couple of states before it reached a kind of regional data center that had a copy of the content that you were looking for. There's a bunch of places in the world where it could travel across countries or across regions before it found the data that you're looking for. And so that's this diagram here. And then what has happened over time is that CDNs have stood up and can cache a copy of that content closer to the end user. And so now that your request for the content goes out from your home, it hits a same router or two with your ISP, but hopefully, and we're getting better at this, hopefully it can find the content in your local metro area. And that's the idea, is we want to be able to just like going to the supermarket, you want it to be convenient, we want to be able to find as much content and services as possible, as close to the user as possible, literally so the data doesn't have to travel as far, and so it doesn't take as long. And so that's the role that CDNs play. I mean, it's not just about performance. There are security and and reliability aspects of it too, but performance is a big one. And it's all in service of, reducing that latency. And so sometimes we fall into this trap of AR and VR needs really good latency. Gamers need really good latency. And operating system uploads or downloads need really high bandwidth. But I want to try to make the case that almost everything that we do on the internet is latency sensitive. And so this is a load of CNN.com. And I could have done weather.com, which is possibly the worst loading. But CNN.com will do the job. And so if you see in here, the first request that it makes, I typed in CNN.com, but the webpage is hosted at www.cnn.com. And so it was 300 milliseconds before that 301 redirect, the redirect from CNN.com to www.cnn.com got back to my browser. So now I know I need to load www.cnn.com. Now I need to get the HTML file. So I go back out to a server and get that file, and it comes back to me. Now I need to know that I need to load a bunch of JavaScript files. And so it goes back out, gets those JavaScript files, brings them back in. Somewhere in there, it has enough data to load the web page, but there's a whole bunch of blocking round-trip requests in there. And so that really adds up, and the more we can compress that latency, the faster we can get this web page to load. So let's see what this looks like with data. This is data from a great paper from some MIT researchers using the FCC's Measuring Broadband America program, which is itself a great data source. But it shows that above about 20 megabits per second, that the web page is not loading any faster, the more throughput, the more bandwidth you apply to it. So I'm not going to use the term speed. I have an allergic reaction to the term speed to describe bandwidth. But this is a real data chart that shows that that your gigabit connection is not helping you load web pages any faster. Compare that to the chart of what happens when you reduce latency, which is the same effect I was showing for CNN.com. It is a linear relationship. The more we can reduce the latency, the faster the web page will load, for the exact reason that we looked at with CNN.com. And that relationship will hold true down to almost zero latency. You can speed up the web page. And so that's it. I think I'd like to close by saying I think that it is any technology that we have that can reduce latency and improve internet performance is good to have. I think we're at the point in the United States where there's about 10% of Americans that don't have access to a broadband connection. There's about 20% of Americans who aren't using the internet. There's probably a little bit more than that whose internet connection is kind of not good enough. As I start to think about how we apply policy to this, how we encourage better latency, I'm thinking about how can we make it so that as all Americans get enough throughput, that they also have a really fast internet connection in terms of the latency. I'll leave it there.
Great, thank you. Next up, we have Ermin.
Thanks, Jason, and thanks for inviting me to the panel. So my name is Ermin Sakic, and I'm with NVIDIA, where I work on the cloud streaming service, specifically for cloud gaming and AR, VR streaming applications. And so I will give a perspective of an ever-growing service, and how latency impacts us, and how other aspects of transmissions over internet can impact the streaming experience and the adoption of the service. And I'll show some data to hopefully undermine. So for those who are unaware what cloud gaming is and what cloud streaming is, basic idea is that instead of having your game or some heavy workload execute locally, perhaps on your MacBook Air, some lightweight device, maybe your Android or iOS phone, you are basically offloading the calculations such as rendering of game frames at perhaps 4K 120 FPS if you want to do so, away from your local device, and instead put that workload in a server farm out there and basically let those frames be transmitted over to your local home network. And you are doing this over internet, which means it's an unreliable link. It might work well in some conditions, sometimes it does not, and we have to adapt to that. But the basic idea and premise here is you don't need to continuously upgrade your hardware, your client hardware, in order to render the latest content that you might be interested in. And also you can save on the battery life, for example, because you don't need to be you don't need to execute complex calculations anymore locally, which again can provide for thin clients and deployment of complex applications on thinner clients than we might have with today's AR devices, for example. You don't need to carry a Tether battery with you, for example. We support different types of games here. So there's like 1,800 games in the library, and there's also a Cloud XR. It's a library which basically allows you to do the same for stereo streaming for XR content, so AR and VR both. And the GeForce Now is the cloud gaming service that I'm talking about here. It's already supported in over 100 countries, and we have over 25 million users confirmed so far. And we do host our own data center, so to minimize the latency aspect of it, if you think about an interactive service, any kind of input that you expect a response to, basically your motion to photon latency, will impact your experience. And so you want to put those data centers as close to you as possible, so we had to distribute and have over 30 physical data center deployments around the world. And each of these will have at least 2 to n different transit links, so to optimize for peering or provide for an optimization peering between the ISPs. And we also have points of presence as the different internet exchange points to minimize the latency. I will show here how the latency can impact user experience. So what we do after every single session, whenever a user starts a game and ends it, they get offered basically an optional rating step where they can rate their service, and we do see a significant inverse correlation here between increasing the latency and the drop in the ratings. So basically, as and I'm showing here on the x-axis the round-trip delays, which is basically our metric for measuring end-to-end latency, specifically the percentile 99. As it grows over to 400 milliseconds here, the expected rating will drop by 30%, which basically indicates that users don't like latency, they will rate it bad, and might even jump away from the service if we end up being in that region which has very high latency. Fortunately, majority of our sessions do stream at less than 100 milliseconds of percentile 99 latencies, otherwise we wouldn't be in business with the service. But there's still a very long tail here on the right. If you look, the distribution shows that there's still a bunch of sessions that end up with high latency numbers, and this is usually coming from home networks and buffer bloats and scenarios that hit and result in high latency. So for us, latency is also not just about networking. There's a system latency involved. I won't go into each of these boxes, but basically each of them are adding latency in your end-to-end flow. So on the server, for example, you might need to capture the frame from a GPU. You might need to encode it and packetize it and send it on the internet. And on the client side, you have to actually assemble that frame. You need to post-process if you need to upscale it, and you have to basically present it on your display, which works with a variable refresh rate, and that refresh rate is adding some latency. And in between all of that, you have the network where you have to transmit the packets in both directions, because we also care about the inputs, so the service is interactive. So all of this adds up to latency. What we can optimize well is the server and the client parts, so the edge parts. But the network in between is something what is out of our control, and that's something that we can adapt to reactively when we observe network impairments. But we basically rely on the infrastructure providers to offer a decent or usable enough service here. On the server and client side, we do things such as 240 FPS streaming to like show you the latest available frames, or do things like frame pacing and stalling in the game engine, so we can synchronize the monitor refresh timing with the frame render timing on the server side and things like that. But network is what adds up a lot of latency. And next to last slide here, I'm basically showing here just a simplified example of a connection. So we might have a streaming server, like NVIDIA on the left, and some other service that's sending data in your home network over internet. And on the very right, you see your home network could be connected over Wi-Fi or 5G, for example. Once we start sending traffic, we have multiple points in the network that impacts us. So one is the packet losses that may come from transit peering. So if there's a bottleneck, there's a Super Bowl being streamed during peak hours, for example, a lot of users watch it on your ISP, there's a high chance that you might encounter worse performance than usual if there's a bottleneck link there in the peering. And on the right side, as we approach the edge where we stream data into the user's network, we start seeing issues such as bottlenecks that Jason mentioned before, that may be related to your plan. You are trying to download more data into your home network than your plan actually provides, so you basically start buffering data in a queue. This adds up latency and is what we usually call buffer bloat. And in order to get around that and minimize latency, there are mechanisms like such as AQM that can be deployed. And on the very right side, we can also encounter latency and packet loss because of scheduling delays where your devices connect your gateway to the Wi-Fi router, for example, or G-Node B in 5G context. Any interference or scheduling delays can also impact your performance. And we need to address all of these. Now, if we cannot do this and we lose some packets and we cannot assemble the frames, then we might need to do retransmissions that are super costly because you need to, again, talk to your server, get a new frame to reference in the future for the future frames, and this is very latency demanding. We can also do error concealment, but this results in picture distortion, and it's not an ideal case. And this is my last slide that I will show. I hope we can maximize it. Can we put it on full screen? So this is just an example of a game called Fortnite, streamed in the exact same bandwidth condition, exact same network. The only difference between the screen on the left and the right is that on the left we don't have an AQM that's latency isolating. We don't have an active queue management mechanism that ensures that our service, that the responsive service gets low latency. Whereas on the right, we have that L4S. And so what you see on the left is a lot of stutter and jumps and frame skips and decoder skips, making for a very unplayable or unenjoyable experience, whereas on the right, you see a super smooth stream. And the latency number on the top right, you see the spikes in the red on the left screen and no spikes on the right. This is basically what we show to the users as an indicator that they have a latency issues, among other indicators yeah, and with that, I will close out. I do have a couple backup slides in case we get to that later. But,
Thank you.
Yeah.
Next up is Nick.
All right. Great. So thanks. As Jason introduced, I'm a professor of computer science at the University of Chicago. I work in network measurement. I've actually been working on designing, building and deploying measurement systems since about 2011, 2012, since the early days of the Measuring Broadband America program. We had this system called the Broadband Internet Service Benchmark, or BISMARK, that we built that to measure throughput way back when speeds digit megabits per second downstream a lot of the time. DSL was still fairly prevalent as an access mode. That project has actually continued. We're still working on that in the same area today, but I'll sort of tell you about the arc of that project and how, sorry to use the word speed, but how it's really kind of evolved beyond just through speed in the traditional sense. I should note, I know this panel's on latency, but I think even in the 2012 days, it became quickly apparent to me that even measuring throughput is not a straightforward exercise. Okay, enough said on that. I only have 5 minutes. But that certainly was an interesting journey in and of itself. I think it was around 2014, I was speaking with some of the folks who were heavily involved in the Measuring Broadband America project at the time, Walt Johnston being one of them, came to me and said, hey, I think in your work you might consider doing a web test, because I think web page load time may actually stop correlating with throughput at some point. There's a lot of discussion about the role of latency, et cetera. I think, Mike, I don't know if that was, that might have been my paper you cited actually. Around 2014, 2015, we had a paper using, we actually helped the Sam Knows folks develop their web speed test and deployed one of our own, and saw that essentially web page load time stopped improving around 20 megabits per second downstream. So kind of confirming the hypothesis of those like Walt. So that was kind of our first exposure to latency as sort of a primary performance metric. That was like almost 8 years ago now, 8 or 9 years ago. And I think the story has really continued from there and continue to evolve, I would say. Around that time, maybe a year or so later, we were approached by some folks at the Wall Street Journal who said, hey, we're getting a lot of people calling us talking about how people are complaining about their video performance, and they're getting advice to upgrade their speed tier connections, and we're not so sure that speed correlates with video streaming quality or video on demand, I should say, quality after a certain point. And so it's kind of the Walt Johnston story all over again, except I guess from the journalist consumer side and a different application. And that was an interesting journey. Because we took on the question of how does streaming video on demand performance correlate with speed, and when does that correlation sort of cease to exist? And that turned out to be a very technically interesting question, because if you're not the video service provider, figuring out things like frame rate, resolution, startup delay, et cetera, actually a little bit challenging to do from network traffic. And we thought, oh, this won't be too bad. We'll just look at the dash protocol. This should be straightforward, except thanks to folks like Jason and others, like a lot of network traffic at the time started to become encrypted. And so that turned out to be a really interesting technical problem of how you infer things like video on demand performance from encrypted traffic. So we did manage to crack that problem and do another deployment where we then we used, so you're not in the AI panel, but you're going to get some AI. We deployed some machine learning models to look at encrypted traffic in about 60 homes, mostly journalists in the New York City area, but a wide variety of ISPs, looking at the correlation between speeds, the throughput, that we could measure from those homes, correlated with video quality of experience for video on demand. And lo and behold, we saw the same kind of trend, except the plateau wasn't at 20. This time it was about 100 or 200 megabits per second. You could really start to see a plateau as far as the things that users cared about: startup delay, resolution, frame rate, et cetera. And then I think that sort of brings me to chapter 3, which is right now, I think with the deployment of fixed 5G, certainly the question again has come to the fore, looking at, well, how does the performance of these kinds of networks compare or relate to other modes of access? And as part of that, I think all of the things that I've talked about kind of led up to not only we continue to be active in our research on this, but in a commercial venture that we've started, we're also exploring what the market looks like as far as different modes of access, and a lot of interesting results there, I'll say, related to latency under load and responsiveness as it relates to the fixed 5G space. So I think for this audience in particular, I'll say that it would certainly appear that some of those fixed 5G providers are showing significantly higher latencies and latency under load, lower responsiveness than our wireline providers, and so it's really incumbent to be looking at these metrics that we're hearing about in this panel as part of the whole user experience package. Okay, I think just a couple of closing notes since I'm at time. I think one of the things I've learned from my my journey in this space over the last 10 or 12 years is that the applications evolve, the network infrastructure evolves, and certainly we're seeing right now that the importance of measuring performance along multiple dimensions is extremely important. But again, I think the needs of consumers continue to evolve. Applications, we're seeing Vision Pro and other things now. These are things that maybe we could have predicted, but we might not have been able to quite predict the specific ways to measure the network to assess what user quality of experience or user experience really is. And so I think there's it's incumbent on our community to design measurement platform suites that are extensible, open source, and also allow us to gain access to public data so that we can really see how these networks are performing.
Great, thank you. So we've got a little bit less than 20 minutes left. I've got some directed questions I'm going to ask our panelists, and then we'll take questions from the audience. The first one is about measurement of this problem, and I think really Mike and Nick are kind of the authorities here. They've done a lot of measurement over the years. I know Cloudflare, has a good speed test, even though you don't like that name, and that data set is now, I think, being integrated into the MLabs data store, which is interesting. And Cloudflare also has something called Radar, which is a website that you can look up different networks and their quality and so on. And I know, Nick, you've looked a lot, particularly lately, about Wi-Fi networks being the bottleneck in a lot of cases. So, question to the both of you, what interesting things have you seen? Nick, you mentioned one of them being, difference between wireless and wireline networks, but what would be interesting from a measurement standpoint, since, mostly these days everybody is just aware of the speed test and really nothing else?
You mentioned the Wi-Fi bottleneck issue. That's another one that, I guess, thanks for the opportunity to talk about that. Another thing that we've done over the past, I guess, 4 or 5 years is develop tests that concurrently measure the user's Wi-Fi with a speed test that's running essentially off the home router. And obviously, the situation is going to depend on the home, but I think that's actually kind of the point, is that a user's home network setting can have significant effects on their experience. I don't have the specific statistic at hand right now, but it's roughly what you would expect as far as Wi-Fi bottlenecks. I will say that as part of our work, like we've done a bunch of deployments in hundreds of homes across the United States in the last 5 years, I'll say, and once again, I think once speeds get above about a gigabit per second, it's almost exclusive in our measurements that the user's performance bottleneck is actually inside the home for throughput, I'm speaking about. And then even you get to slightly lower speed tiers than that, or speeds, and it's still, by and large, the Wi-Fi that's actually a limiting factor, and I think we could certainly talk a lot more about that.
I guess just briefly what I would say is we're measuring the kind of application latency between somebody requesting our content and our services and kind of the round trip time to get back to them. There are there are places in the world where a new POP, a new data center that attracts that traffic is just totally transformative to their internet experience, because the traffic isn't kind of leaving countries and continents. I think in the U.S. we're in a better position on that, yet still, here's an example. A couple years ago, the city of Montgomery, Alabama launched an internet exchange, and the city put a whole bunch of time and effort and a little money, not too much, but a little bit of money into that internet exchange. And that has the ability, if it attracts enough networks, and if it attracts content and services networks on one side, if it attracts internet service providers on the other side, to make it such that somebody in Montgomery, Alabama can find their streaming game or anything else in their local market, and their traffic isn't backhauled to Atlanta or Dallas. And the same that happens in the South, and it also is happening quite a bit in the Midwest, in Iowa and the Dakotas and some of those states. That the traffic has to kind of go a great distance, and so I'd say one of the things that we can measure is what is the latency by ISP and then by state, to make sure that is one of the things that's taken into consideration as we deploy new networks.
Yeah, that's a really good point, especially given the FCC's focus on middle mile grants, through the BEAD program, and this need in the content to get sort of hyper local so that it's the shortest round trip time. So moving on, Ermin, I wonder what you think about not just the customer impact when you're, say, gaming and you encounter this high latency, but what other kinds of applications, from your standpoint, become possible? We've got someone that's, here from Apple. They have the Vision Pro headset, which is taking the world by storm. And, you have older generations of other companies that, people describe like VR motion sickness and these kind of things.
Yeah.
So what do you think in terms of applications that become, really possible now in the future with ultra low latency?
Okay. So I mentioned before that AR/VR, a use case where we're basically streaming the app itself, including some production tools. We have a product there called Omniverse, basically for like 3D modeling, CAD type of applications, streaming that in low latency properties, ensure high throughput, high fidelity, and possibly also to an AR, VR enabled device, so to an HMD like provision. Something like this becomes possible once you can guarantee below 20 milliseconds round trip delays, and ideally sub 10 milliseconds latencies. Another interesting application is teledriving, for example, where there's a startup called Vay, which has demonstrated recently also an example of L4S with, I believe, Ericsson and Deutsche Telekom, that it's possible to have kind of a semi-autonomous solution to resolve today's issues around AVs. So that basically their use case is you deliver a rental car to your place, and you pick it up while having a remote connection, remote driver also in the loop that's capable of reacting faster than, or with some responsibility and the person in the loop, given if the network is also supporting it. I don't think we are quite there, so that's a wide, that the network widely enables this today, but they have already demonstrated it on different streets in Europe, for example, with an L4S and 5G G-Node B setup. And I think that said, cloud gaming is growing for us, and one, I think, important observation there that we kind of miss often is you don't always need the lowest latency at all the times. What very much matters for us for good experience is consistent latency. So jitters and latency variation makes for a very unpredictable service and performance. Like I mentioned, motion to photon latency before. When a user clicks, when you make a keyboard type, and you expect a feedback loop to kick in at some specific time in the future, this doesn't work if you have constantly spikes in your latency. So even though your average latency might be low, any spikes will give for an intermediate poor performance and poor experience. For us, consistent experience is very important. And again, depending on the content, it also becomes obvious if you're playing, a strategy game, some like slow content, or even some professional visualization application versus streaming a first-person shooter. You might be perfectly fine with having 60, 70 milliseconds fixed latency versus having low latency at the times, but then spiking up to 200-300 milliseconds in between.
So predictably low latency.
At least predictable moderate latency is what can make for a decent experience. Ideally, we will always have a low latency and have it consistent. Upstream latency matters too. This is in contrast to something like Netflix that might be, serving the content which might be slightly buffered, but you want to deliver it as fast as possible, so benefits from latency. But for us, upstream bottlenecks are also very important. So if you have, and we do see a lot of asymmetric deployments in terms of bandwidth in the US, which is also a technology limitation to some extent, but having AQMs and mechanisms that enable low latency on upstream is very critical for these kinds of applications because there's an input involved there.
Yeah, and that's a good point to mention AQMs, which for those of you that don't know what that is, that's active queue management. It's a form of TCP congestion control, and network equipment can embrace that and deploy it now. Comcast has it deployed in our gateways and cable modems. Other people can do it. And there's lots of variety of AQMs. Pi is one of them. DOCSIS has an implementation of that. There's FQCodal and others that exist out there. And so there are things people can do in particular to try to improve their network now. I'd like to go to one last question before we open up to the audience. And this is one really for Dominique about the policy implications that you talked of a little bit ago. And I can tell you from somebody who's been at Comcast for a while, my sort of baptism by fire in the tech world was the BitTorrent incident, so to speak. And we had a little bit of a problem with peer-to-peer traffic. And as it turns out, as we understand it now, that was a working latency problem. That was buffer bloat. Just completely misunderstood, solved in a bizarre way that wasn't great. So lots of lessons learned. In a difficult way, but as a result, now we have net neutrality, thankfully, right? So I guess you can really blame latency for that. But what are your thoughts about this? Like, is it ultimately, especially in the European and UK context, is that a specialized service? Or is it just, because it's applications embracing it and marking their traffic for it, does it become, just sort of an okay thing? 'Cause since we know that, Europe and the UK are always sort of further, on the spectrum of regulation.
Yes, that's true. Thanks. Just one comment I want to make on IXPs. I've been able to see just in Africa and some of the sub-Saharan countries, just going from 0 to 1 IXP, how much of a difference that makes. I mean, we're lucky here, but it's unbelievable, especially around just getting content. And I just wanted to highlight that because it's been incredible to see that. But thanks on the policy and regulation side. So a couple of things I have to say, and I sort of hinted at it. The regulation is old, right? That's why there's been consultations in Europe and the UK most recently. But in Europe, the regulation is old. Like, this wasn't really even an issue back then. And as we have more VR coming on board, there was a working group on autonomous vehicles within Europe most recently. All of this is post-2015. For the directive. Again, each country within Europe puts the directive into their law in a different way. There's quite strict net neutrality laws in the Netherlands, for example. And so you'll see different, and there's more technologists, I would say, that have worked on the law. So it's really quite a very different approach depending on the country. However, I think that most of this is seen as active technical traffic management. And I think that as all of you work on developing more and different ways to manage traffic, I think engaging with policymakers is going to become ever more important throughout global rollout, but also throughout 5G, 6G rollout, which is coming. The 6G standards are starting, and then again the impact and effect on not just Starlink, but other providers, satellite providers. I mean, I know that I spend most of the summer using Starlink, right? So how is that going to impact me, or how am I going to be able to use that? And so there's multiple technology questions that have multiple policy implications. But I think with the review, like what the UK undertook and the approach that it's taken, it has some pretty solid and quite good engineers internally at Ofcom, but also they liaise quite closely with their industry because it's just a smaller country more than anything else. You're starting to see the understanding of having flexible regulation that has, I don't like to say, level playing field, but has a pretty low sort of monitor or level of regulation where you really can do innovation. So I think what comes to mind when it comes to this is I think about a content provider, having CDNs or working, within a local community and how they are able to contract financially and how they're able to set up their terms, and being able to provide that flexibility for each of those companies as the technology changes is really, really important. So the bottom line answer is I think net neutrality is what's regulating it, but I don't think it's necessarily appropriate anymore.
Okay, great. So questions from the audience. What do you want to know? What questions do you have? We've got two folks right here.
Hi, thanks. I have two questions. I don't know if I can ask both or just one. The first one relates to what Ermin showed about AQM in the context of a home network, so a private network. Jason, you just explained that ISPs can deploy AQM in order to improve traffic management. How can the orchestration of different requests for different AQM classes, I guess, work in a way that keeps this loose coupling that you described between applications and networks? And how is that consistent or not consistent with different views of net neutrality?
Right.
That's the first question. And if I may, just a second question was more for Nick around the comment you made about 5G FWA networks potentially exhibiting higher latency under load. Mm-hmm. This morning, Commissioner Carr said, whatever we do, we need to be tech neutral. And obviously, one of the questions is, can you specify latency under load thresholds in order to preserve tech neutrality and yet get the performance that we want to get from gigabit networks? Thanks.
Got it. So I'll tackle the first one about the marking. The way that it works, there are two different IETF standards for how you mark. One is in the ECN part of the packet header, and the other is the DSCP part of the packet header. And any application can mark. It's documented in the ECN part in 3 RFCs, and the other part for DSCP coming soon. I think the internet draft is on probably the 18th iteration. So really, any application can just apply those marks in the client. And then any network hop that implements that standard will put it into this separate queue. And so, totally open from that standpoint. And then the second question was around 5G fixed wireless. Anything in particular about tech neutrality? I noticed, even though the bandwidth is good, you've noticed in your measurements, substantially different and highly variable latency.
Yeah, I don't know. Maybe I'm going to get ejected from the city for saying this, but I don't know. I mean, I think that phrase is ridiculous. I mean, that's like saying, let's be tech neutral. We should consider carrier pigeon and old school modems and DSL as well. If the performance metrics don't line up to things that deliver a good user quality of experience, then that needs to be front and center. I mean, I think there's a difference between saying, let's not put our thumb on the scale for one technology versus another as far as maybe regulation or as far as regulation is concerned, but it's a completely different thing to pretend that these are one and the same type of technology delivering the same experience for users, because at the moment they're not. And so, sure. I mean, I'm sure there are a lot of smart people working on improving latency for fixed wireless technology, but I can tell you right now from what I see, it's not there yet.
So next question, we had Harold in the queue.
So I'm going to ignore net neutrality entirely and focus on my other obsession, which is Wi-Fi and unlicensed spectrum, where I was very interested to hear about something we all sort of generically know, which is the problem inside the home network, where increasingly it is, number one, impossible to find devices that don't have Wi-Fi capability, where the default is that it is on so that it can report back to various motherships about how many times I run my washing machine or whatever. And just the number of devices like these pads and phones that won't connect to a, I'm curious, is there, number one, a way within the Wi-Fi protocols itself? Is it something that you go to Wi-Fi Forward and say, hey, for Wi-Fi 8, can there be some kind of traffic load management that, works to help reduce the latency as we move across the networks here? Or is this if people are going to insist on doing this, we're going to need bigger channel sizes, which has been the solution of Wi-Fi 6 and Wi-Fi 7, which means finding more unlicensed spectrum that can be used for Wi-Fi routers?
Yeah, I think there may be a few answers there. One, a lot of the Wi-Fi standards to date have been heavily optimized towards maximizing throughput, like many things, right? And so the current versions of Wi-Fi do have a notion of different sort of priorities. There's best effort, and video and voice and background. But that's really just, relative priority, like quality of service, not really low delay. It is something that, there is in discussion for future versions of the standard, and I hope that we'll see more alignment between the sort of marking that IEEE uses and IETF use, so that's sort of one of those challenges. But I would say, to your first question, probably the most important part is more Wi-Fi spectrum, more unlicensed spectrum. I think you could have a huge impact on, everyday Americans' internet performance by having more access to unlicensed Wi-Fi spectrum. That's the primary way that every single device connects. Even if you think about a mobile phone, like on our network with Xfinity Mobile, something like 80 or 90% of the time, that is connecting over a Wi-Fi network, not over a 5G network. So I think all of that argues for, a lot more unlicensed spectrum in the home and, as a really important aspect. Any other comments on Wi-Fi?
I mean, just even with the C-band, we don't have the C-band problem that you have here in Europe. I mean, just even releasing some of the C-band will actually free up a lot more innovation, I think. And it's kind of a little bit of a shocker to see that that's still a discussion when I come over.
So we've got a couple more questions over here. Go ahead, Sol.
Yes. So lunch is starting now in the main atrium, but I think we have time for one more question.
All right, we've got one final question.
Nick, you were a button pusher. I've been running a fixed wireless network for 25 years, so thanks for that. And the reason we haven't been scaling is because the FCC has been allowing all of the spectrum to go to the licensed carriers. In fact, the $3 billion record sale they made to Verizon, 3 months later, Ajit Pai, their lawyer, who was the chairman, gave them $5 billion grant. So you can't tell me that it's fair. They've been making sure that fixed wireless couldn't grow because we already have the customers and corporate is doing their best to take it over. But you can't always blame the ISP either. Much of the modern latency is old computer operating systems, 100 megabit cards, Ethernet cards and computers, improper placement of home routers, and of course we play the game with Okula where we do bursting so that they have their own speeds, and of course Okula itself doesn't work because it only uses available bandwidth, and the only people who run available bandwidth tests is when they're gaming or streaming, so it shows extremely low, which is the way to show that it doesn't work. Really, industry programmers, regulatory agencies need to stop the pendulum swing of excessive control. Net neutrality is throwing 1934 laws on internet providers who were lightly touched before. There's something at the FCC called the B permitting that simply makes sure that you're not slowing down people between technologies like Apple does with their texting to Android and things like that. That's the kind of stuff that we need to work towards. And the people who are the technical industry people need to be making true assessments of speed and looking at the home user capabilities at all, because now the FCC wants to call an inability for a customer to get the speed, digital discrimination, and they can sue us. So I could get a slap suit, wipe out a community ISP, and that's one less competitor against the corporate giants.
All right. Any reactions or comments in our 1 minute?
Yeah, I'll just respond to that. So it wouldn't be a panel without a little controversy. But I think I think it's. I enjoyed your comments actually because as someone who does performance measurement, I see the outcomes and outputs. But I think your comments were really on the shape of the industry and in the context and the inputs and like what results in what we see on the outcomes, which is something that I don't spend a lot of time thinking about. And I think like one of the just to sort of get back on my own soapbox, I think one of the things that that I hope is that measurements that we can all kind of agree on are a good representative set of like what users are seeing from different providers. That might actually help everybody tell their story. Everybody seems to have a different story to tell, a different agenda, except I think maybe we can all agree that improving the user experience is one that we'd like to all achieve.
Cool. Well, thank you to all of my panelists. Really appreciate your time and your travel today. Thank you also to our audience. I was very impressed. No one fell asleep. That's a really big deal. But lunch is available outside, and happy to take any questions that you may have afterwards. Oh, and I'm told there's a salons later, and you can sign up outside of the North Room. See, I got that right. That's great. And if you're interested in that, that's where you sign up. I don't know what they're discussing, but you can find out, I'm sure, on the agenda. Thank you.